Operators work with math as a routine part of their jobs, but not all math is simple arithmetic. For instance, this operator must use a formula to determine how fast material is flowing out of a tank. And because this operator knows how to analyze a chart, he has detected a problem in the value of a process variable. An area describes the number of square units contained within a flat surface. The shape of that surface is what determines which area formula should be used. In this part, we're going to look at the formula for the area of a rectangle and the formula for the area of a circle. Let's begin with the rectangle. The formula for the area of a rectangle or a square is area, A, equals length, L, times width, W. For example, this rectangle is 15 feet long and 12 feet wide. 15 feet times 12 feet is 180 square feet. So the area of this rectangle is 180 square feet. Another common area formula is the formula for the area of a circle. The formula we'll use is area A equals pi times the radius, r, squared. Pi is a symbol for a constant value that is approximately equal to 3.14. The radius of a circle is the distance from the center of the circle to the edge of the circle. If a circle has a radius of 3 feet, its area is pi times 3 feet squared, or 3.14 times 9 square feet. So the area of this circle is 28.26 square feet. A volume describes the number of cubic units contained within a solid. Basically, volume is a measure of a three-dimensional object or space. Volume formulas are helpful for figuring out things like the capacity of a vessel or the amount of material in a tank. The formula for the volume of a rectangular container is volume, V, equals length, L, times width, W, times height, H. To find the volume or capacity of a rectangular tank that is 15 feet long, 11 feet wide, and 10 feet high, we multiply 15 feet times 11 feet times 10 feet, and find the volume of the tank to be 1,650 cubic feet. To determine the volume of material in the tank, we can substitute the level of the material for the height of the tank. For instance, if the level of material is 6.8 feet, then the formula becomes 15 feet times 11 feet times 6.8 feet, which equals 1,122 cubic feet. Now, not all tanks are rectangular. Many tanks used in industrial facilities are cylindrical. To find the volume of a cylindrical tank, we use the formula for the volume of a cylinder. Volume, V, equals pi times the radius, r, squared, times the height, h. You may recognize pi r squared as the formula for the area of a circle. This is used because the base of a cylinder is a circle. To find the volume or capacity of a cylindrical storage tank that has a radius of 7.5 feet and a height of 30 feet, first substitute the numbers in place of the letters and symbols in the formula. Pi is the constant 3.14. R, the radius, is 7.5 feet. 7.5 feet squared is 56.25 square feet. H, the height, is 30 feet. 3.14 times 56.25 square feet times 30 feet equals 5,299 cubic feet, rounded to the nearest cubic foot. The volume of material in the tank is calculated the same way as with the rectangular tank. Simply substitute the level of the material for the height of the tank. In this part, we're going to look at formulas for volumetric flow rate. But first, let's define a few terms, beginning with rate. A rate is a comparison of two quantities through division. One of the two quantities is often a unit of time. A common rate used in operations is a flow rate. Flow is the movement of a stream of material. Flow rate is the amount of material that is passing a specific point at any given time. There are two basic types of flow rates: mass flow rates and volumetric flow rates. Mass flow rate is measured as a unit of mass, such as pounds, per a unit of time, such as hours. For a volumetric flow rate, the amount of material is measured as a unit of volume per a unit of time, such as cubic feet per second or gallons per minute. A general formula for volumetric flow rate is V dot equals V over T. The dotted V is used to represent volumetric flow rate. The other V stands for volume, and the T represents time. For instance, if the volume is 150 gallons and the time is 1 minute, then the volumetric flow rate is 150 gallons per minute. Volumetric flow rates are often determined for materials flowing into or out of containers. This is a general formula that can be used to calculate the volumetric flow rate when material is flowing into a container. V dot in represents the volumetric flow rate into the container. VF is the final volume, and VI is the initial volume. T stands for the time between the initial volume and the final volume. For example, this tank contained 12,000 gallons to begin with, and it now holds 15,200 gallons. We know that no liquid was removed, and it took 4 hours to fill the tank to this level. If we put these values into the formula, we find that the volumetric flow rate equals 15,200 gallons minus 12,000 gallons divided by 4 hours. 15,200 gallons minus 12,000 gallons is 3,200 gallons. Divided by 4 hours is 800 gallons per hour. Now, if material is flowing out of a tank, the formula changes. Volumetric flow rate out, V dot O, equals initial volume, VI, minus final volume, VF, divided by time. For example, we know that a tank contained 1,500 cubic feet of material at 8 a.m. No material was added. By 10 a.m., the tank contained 950 cubic feet, and from 8 a.m. to 10 a.m. is 2 hours. So, using the formula for volumetric flow rate out, we have 1,500 cubic feet minus 950 cubic feet divided by 2 hours. 1,500 cubic feet minus 950 cubic feet is 550 cubic feet. Divided by 2 hours is 275 cubic feet per hour. In this topic, we discussed formulas. Specifically, we looked at the formulas for the area of a rectangle and the area of a circle. We also saw the formulas for the volume of a rectangular tank and the volume of a cylindrical vessel. And finally, we saw formulas for volumetric flow rates. Now try some practice questions to check what you've learned. The formula we'll use is area A equals pi times the radius, r, squared. Pi is a symbol for a constant value that is approximately equal to 3.14. The radius of a circle is the distance from the center of the circle to the edge of the circle. If a circle has a radius of 3 feet, its area is pi times 3 feet squared, or 3.14 times 9 square feet. So the area of this circle is 28.26 square feet. To find the volume of a cylindrical tank, we use the formula for the volume of a cylinder. Volume, V, equals pi times the radius, r, squared, times the height, h. You may recognize pi r squared as the formula for the area of a circle. This is used because the base of a cylinder is a circle. To find the volume or capacity of a cylindrical storage tank that has a radius of 7.5 feet and a height of 30 feet, first substitute the numbers in place of the letters and symbols in the formula. Pi is the constant 3.14. R, the radius, is 7.5 feet. 7.5 feet squared is 56.25 square feet. H, the height, is 30 feet. 3.14 times 56.25 square feet times 30 feet equals 5,299 cubic feet, rounded to the nearest cubic foot. This is a general formula that can be used to calculate the volumetric flow rate when material is flowing into a container. V dot in represents the volumetric flow rate into the container. VF is the final volume, and VI is the initial volume. T stands for the time between the initial volume and the final volume. In this part of the program, we'll take a look at charts and see how they can be used to obtain information about process variables. Operators routinely use the charts from chart recorders to obtain information about process conditions. When a chart recorder is operating, its chart shows current operating conditions as well as the operating history of a system or process. When one chart has been used up, it is removed and replaced with a new one. But old charts are usually saved since they give information about past operations. One common type of chart used on recorders is a strip chart. A strip chart is a long strip of paper. When this type of chart is placed on a recorder, the chart is advanced by a drive mechanism that moves the chart across the face of the recorder. The strip chart has horizontal and vertical lines that form a grid. The horizontal lines on the chart divide the chart into units of time. Here, the units are increments of 30 minutes. The vertical lines represent values of one or more process variables. A single strip chart may show values for several different process variables. On some recorders, the values of different process variables are all recorded on the chart using different colors to represent the different variables. A key that identifies the variables and their colors on the chart is provided on the front of this recorder. On this recorder, red indicates deaerator north level. On some other recorders, numbers as well as colors are used to represent the different variables being recorded. The key on the front of the recorder identifies which colors and numbers are assigned to which variables. You can read the chart by color, or when the number of the variable you want to know about appears on the recorder, you can read the value that is then being indicated on the scale. The scale indicates the values of the process variables that are being recorded. Another kind of chart that is frequently used in industrial operations is a circular chart. A circular chart is divided into an equal number of sections for the amount of time over which information is being recorded. This chart for a 24-hour period, for example, is divided into 24 one-hour sections. The numbers on the inner portion of the chart represent values for the process variable that's being monitored. When the chart is placed on the recorder, it is rotated by a drive mechanism. In the case of the 24-hour chart, the drive mechanism rotates the chart one complete revolution in a 24-hour period. Some circular chart recorders record values for only one process variable. Other circular chart recorders can record values for several process variables at the same time. A pen that's attached to an arm on the recorder is used to mark the chart. If values for more than one variable are being recorded, more than one pen is used. Each pen has a different color ink to mark the values for a different variable. Graphs are visual indications of numbers and relationships between numbers. When the numbers represent values for process variables, graphs can show the relationships between different operating characteristics of systems and equipment. One of the most common graphs used in industrial operations is the XY graph. This kind of graph is formed by two intersecting lines. The horizontal line is called the x-axis. The vertical line is called the y-axis. The two axes are generally marked off with different units of measurement. On this graph, the x-axis is marked off in pounds per square inch, and the y-axis is marked off in degrees Fahrenheit. The line shown on the graph is called a curve, regardless of whether it is actually curved or straight. The curve represents the relationship between the variables on the two axes. A graph can be used to determine the value of one variable that corresponds to a value of another variable. To understand this better, let's look at how to read a graph. First, locate a value on one of the axes. For example, 200 psi on the x-axis. Then follow the line from it until you reach the intersecting point on the curve. From that point, follow straight across to the opposite axis and read the value there. By following a line from the curve over to the y-axis, we find that the y value that corresponds to 200 psi on the x-axis is 100 degrees. The x and y values on this graph can be written as an equation. This curve represents the equation y equals x minus 100. If you know the value of either x or y, you can use the equation to calculate the other value. For example, if we substitute 200 for the x value, we find that y equals 200 minus 100, or 100. Drawing curves on a graph is referred to as plotting the graph. Graphs are often plotted to show the relationship between two process variables. For instance, in our example, temperature and pressure. The first step in plotting a graph is to gather and organize the information that's needed to plot the x and y values. This information, or data, can be obtained from sources such as operation logs and process instrumentation. Once you've collected all the information, it's helpful to set up a table and list the X values in one column and the corresponding Y values in another. Next, set up the X and Y axes with the appropriate scale on each axis. The next step is to mark the X and Y values, or coordinates, on the graph. There are several ways to do this. One way is to locate the X value on the X-axis, for instance 100 psi, and follow that line up until you reach the corresponding Y value, in this case 200 degrees Fahrenheit. Place a dot at that location. With the coordinates 200 psi and 250 degrees Fahrenheit, the next dot is placed here. This process is repeated until all of the coordinates are plotted. The last step is to connect the points to form a curve. An XY graph can show more than just two variables. This pump characteristic curve graph shows the relationships among several pump operating characteristics. We can read values for efficiency and horsepower on the Y-axis and the capacity or flow rate of the pump in gallons per minute on the X-axis. Another type of XY graph is a bar graph. A bar graph can be used to compare many different quantities, with each quantity represented by its own bar on the graph. This bar graph shows the amount of a product produced each month for 4 months. This circular graph is called a pie graph or pie chart. A pie graph is typically used to compare the various parts of a whole to each other and to the whole. This graph shows the relationship between the total production of Unit 1 and the amounts of individual products produced by that unit. A nomograph is a graph that uses 3 or more different scales to represent the values of 3 or more variables. When a nomograph is used, an unknown value can be found by drawing a line through 2 known values. For example, if we need to know how much of a material must be added to a mixture to make a product, we might use a nomograph like this one. We can find how much of material B must be added to 300 gallons of material A and 8.0 pounds of material C by drawing a line through the marks for 300 gallons and 8.0 pounds. The point where this line intersects the material B scale is 56 gallons. This means that 56 gallons of material B must be added to make the product. A trend is a consistent pattern in the value of a process variable over a period of time. In a plant, a trend is often defined as a gradual increase or decrease in the value of a process variable. Some of these trends are expected. They occur normally as a system undergoes controlled changes. For example, in a batch operation, process systems may be operated for a certain amount of time, then shut down, and later started up again. This pattern forms the expected trend for operation of the process systems. Expected trends can be predicted. Operators can prepare for them by making any necessary adjustments to operations ahead of time. Some other trends are not expected. These unexpected or abnormal trends are the results of unplanned changes in system or equipment operations that might happen at any time. Such trends may be warnings that problems are occurring or could develop. Before you can take steps to bring operations back to normal, you have to be aware that an abnormal trend exists. Let's take a look at how to go about detecting a trend. The basic reference point for trend detection is normal operation. It's important that you first become familiar with normal equipment operation, normal instrument readings, and what normal operations look like on charts and graphs. If you're familiar with the normal operating conditions, you're less likely to mistake a natural fluctuation for a trend. A natural fluctuation returns to normal in time. However, in some cases, a change in the frequency of fluctuations or a fluctuation that continues until it approaches or reaches a limit could be considered a trend. If a trend indicates that the value of a process variable is approaching or reaching a limit, the situation will have to be analyzed to determine what, if any, corrective action should be taken. A limit is the boundary of an acceptable range for a process variable. Trend analysis is the term used to describe the process of figuring out what a trend means and determining any adjustments that should be made. There are 3 basic steps involved in trend analysis: determining the significance and probable cause of the trend, finding out what, if any, corrective actions to take, and evaluating the impact of those actions before making any adjustments. This control room operator, for instance, has noticed that the reading on the chart for cooling water temperature has been steadily increasing. The first step is to determine the meaning or significance of the trend. From his knowledge of the system, the operator knows that a continuous increase in the temperature of the cooling water could cause problems. Equipment could overheat and be damaged. Process operations could be disrupted, and product quality could suffer. According to the trend shown on the chart, the temperature has risen steadily from the normal 70 degrees to an unexpected high of 76 in the last 3 hours. From 70 to 76 degrees is a 6-degree increase. 6 degrees divided by 3 hours is an average increase of 2 degrees per hour. For this system, a temperature of 80 is the high limit for the cooling water. From the current 76 degrees to the limit of 80 is 4 degrees, and 4 degrees divided by 2 degrees for each hour is 2. If the temperature continues to increase at the current rate, the limit will be reached in 2 hours. Now the operator has an idea of the amount of time he has to work with as he continues to analyze the trend. He checks the inlet temperature of the product that's being cooled by the cooling water system and finds that it has also increased. This would account for the increase in the cooling water temperature. The high product temperature indicates that there is a problem with the production process that will need to be corrected. But in the meantime, the cooling water system must continue to cool the product. The next step is to determine what actions or adjustments are needed to correct the situation. In this case, the second fan in the cooling tower can be operated until the problem in the production process is corrected. Before making any adjustments, the operator needs to evaluate the impact of the corrective action. He should check process instrumentation and facility procedures to make sure that any actions taken will be the proper ones. Well, in this topic, we've covered graphs, charts, and trends. We saw how graphs and charts can be helpful in monitoring a process. We looked at examples of an expected trend and an unexpected trend. We also saw some procedures for detecting and analyzing trends. Now is a good time to try some practice questions. The strip chart has horizontal and vertical lines that form a grid. The horizontal lines on the chart divide the chart into units of time. Here the units are increments of 30 minutes. The vertical lines represent values of one or more process variables. A single strip chart may show values for several different process variables. A nomograph is a graph that uses 3 or more different scales to represent the values of 3 or more variables. When a nomograph is used, an unknown value can be found by drawing a line through 2 known values. For example, if we need to know how much of a material must be added to a mixture to make a product, we might use a nomograph like this one. We can find how much of material B must be added to 300 gallons of material A and 8.0 pounds of material C by drawing a line through the marks for 300 gallons and 8.0 pounds. The point where this line intersects the material B scale is 56 gallons. This means that 56 gallons of material B must be added to make the product. Trend analysis is the term used to describe the process of figuring out what a trend means and determining any adjustments that should be made. There are 3 basic steps involved in trend analysis: determining the significance and probable cause of the trend, finding out what, if any, corrective actions to take, and evaluating the impact of those actions before making any adjustments.